we will ask also Yuri some questions. Okay, let me give a floor to our discussion leader, Professor Atsushi Nakamura. Atsushi, do you hear me?
Yes, yes, yes.
Very good.
Can you hear me?
Right. We hear you.
Okay.
So we now show your slides.
Uh-huh.
Right? Wait a second. So this discussion session covers all 4 talks of this morning session. And Atsushi, please.
Yes. Okay. So for people's okay, I think already many questions for each talks, or you said maybe we can show via yes.
Later, if there are questions asked via chat, then we'll show later. So please start with
okay.
you, and we come to questions.
Okay. Yes, really very interesting. Yeah, and yeah, I should say very informative and yeah, sessions, and indeed for talks covers, but from different aspects or different view. And okay, the first Thomas, he treat or discussed dense quark matter and using effective model, and really I was very impressed. Okay, especially Nambu-Yonaru model. Okay, it's a very old model and was studied many times, many years, but yeah, it's quite still non-trivial, and it can provide us many insight of the QCD. Yeah, and Professor Irina Alefna, and I don't have enough knowledge about holography approach. Then if I can ask here, I want to ask her, so holography approach can be applied to, in principle, anything. I mean, even in the non-equivalent state, or it can be applied just the equivalent state, or yeah, maybe it's a stupid question, but
okay, thank you very much for your question. In principle, the holographic approach can be applied to everything which is, in some sense, is close to conformal invariance, not possess exactly conformal invariance, but very close. And it can be applied for stationary case. In this case, we suppose to use 5-dimensional background, which is stable, not time depending, or you can use it to thermalization. So it means not stable. This is more challenging because it is difficult to discuss, to use our method. Of course, we can use kinetic equation, but this is I understand, rather complicated method. What is the privilege of geographic approach? That you can use it as QCD, heavy ions, as well you can use it in low dimensional case, in solid state. And in this case, there are essentially more methods are available. So we can check how it's work. So this is this is a positive feature of garographic.
I see. So it has a very, yes,
This is very powerful and
powerful and future.
yes,
Yes.
and very it's tested very well for in some condensed metaphysics. And also we can reproduce many interesting features in four-dimensional case. And this is a phenomenological method. So as any phenomenological method, we have to have some input. So we use lattice calculations. We use a lot lattice calculation because the lattice calculation, this is our, how to say, fixed point for mu equals to 0 for no time dependence. This is a very important for us. And is close to garographic QCD it is known that from lattice, for example, then at large temperature QCD show conformal invariance. So if you calculate the trace of the mu on the lattice, you see when temperature increase, then more your model, your lattice model become more and more close to conformal invariance. This is one of the reasons why we can use garographic approach to describe theory of non-zero temperature.
Okay, I see. Thank you. And
for your question, yes.
Yeah, but now, okay, just I would like to ask also, Maria, are you here or?
Yes, Atsushi. Hi again.
Hi. I think, yes, in your talk, yes, you mentioned the application of the machine learning and also, yes, quantum computing, but you skipped the detail, right? So,
no, yes. Thank you for getting back to this. I haven't really touched upon these points. These are really very important, but I considered that we don't have yet real solid results. I can tell you a little bit more about both of them. So machine learning is more advanced, and especially what attracts me most is the possibility of studying via machine learning phase transitions. So as you probably know, I know there is this nice work, for instance, Vladivostok, Denis Boyda, very beautiful. I think you were in that paper too. And so there is this possibility of observing, basically identify different phases, and this is very fascinating. Even most fascinating, something that for me was really fantastic, there is a beautiful paper on Nature, and that was on a easy engaged model, so models which don't have local order parameters, and so there is no phases that you can visually identify, right? I have done work with machine learning myself, studying the confinement transition in QCD by using Polyakov loop, but of course in those cases we can identify visually the phases, so it's very good. But even human, I look at configuration, say, okay, this is broken, this is not broken. But when machine learning really work with this gauge model, and there is no local order parameter, and so the phases are clearly identified from the behavior of 2 points correlation functions. So it's clear identification, but also very subtle. And then when you see that a machine learning model can really identify these two different phases and see the phase transitions, this is quite amazing. And what, of course, I would be very much interested in this machine learning is really to discover phases that for us is difficult to see. And can give you two examples in QCD. We have found this strong fast crossover at around 300 MeV. Many people have observed in different ways. For instance, with Anton Trunin and Andrei Kotov, we observed this threshold because we see that this is the threshold of the scaling window, and it is also the threshold for the dilute instanton gas approximation. So 300 MeV is a threshold in the plasma, but we don't know why. We are looking with Vitaly Borniakov, perhaps there are monopoles, perhaps there are other effects. Well, I really would love to look with machine learning and see whether we can really see two different phases. But I mean, this is very speculative at the moment. We haven't found anything. It's very exciting and promising, but nothing new at the moment to say.
Yeah, I was shocked because yes, I talked with my friends. Okay, let's do something. Yes, completely new. Other people never thought, but you already pointed out this possibility. So yeah, so using these machine learning and also quantum computing. Yes,
now quantum computing is again a different story. Actually, for machine learning, we have I think we have this report, and Andrea Tenodoro has written this part with Gerd Hartz. It's really lots of work going on. There are other applications of machine learning of different kind in lattice field theory. This is a different philosophy. I am more attracted by this phase transition speed, but there are also other applications to speed up algorithms. Quantum computing is yet a different story because it is even more in its infancy, but it may really be the way to go for finite density. But it's really very much behind. There are people in Italy in condensed matter. They really work very hard. They're really very good. There are experiments in tensor network, but I don't see anything at the moment appearing beyond 2 dimensions. So which is, I mean, it may be the way to go, but at the moment, it's hard, but it's something to follow for sure. Thanks for the question. I think these are the most exciting things at the moment. So that's why I thought I should at least mention, but I don't think I would have had anything really useful to say for this meeting here. Thanks.
Okay, and just short question about you, Yuri. Are you here? Hello.
Yes, Atsushi, I'm here.
Yes, okay, thank you. Yes, yes. So at least now from the experimental data, okay, of course, you are, very rich experimental data, very impressive, but still no indication about the real, critical QCD, critical point, or so.
For critical point, we should go to the low energy experiments. So this is the future facilities, Nika, Indudna, and FAIR. And at the Rishi energies, we achieve almost zero biochemical potential. So this is very far from the critical point.
Very high energy.
We simply study another part of the phase diagram. So that is why our experiments do not contradict each other, we simply complement each other. And at RIG, there is also an ongoing program of the low energy scan. So they try to reduce the RIG energy down to few GeV in the central mass system. Intensity, the luminosity of these small beams, small energy beams is very low. So that is why they don't have much statistics. But at least they're trying to do something and search for the critical point.
It's possible, and
it's possible, but I think we have to wait 2-3 more years for the first experimental results.
Okay, thank you. Okay, so Vitaly, okay, just could you show the next slide? Just only 2 slides, but I prepare 2 slides and second.
Just wait a second.
Yes. Yes, and so for people, for colleagues, really they choose different approach. Yeah, of course, but why you choose this approach, and why you think your approach is yes better than other one? Just could you tell me in one word?
But please define the order of answers.
Okay, so just from yes the first Thomas, can you tell me why you choose not choose? Okay, you studied effective field theory, or it's of course effective field theory. There is a limitation, but you believe we can get yes much information about QCD or the QCD phase transition, right? Hello.
Yeah, I'm not sure. Maybe Thomas is not connected to us. So let's proceed further.
Okay, then how about Irina? Why holographic
Okay,
approach
very
is
good question. Before working with galography, I work
uh,
on many things, but just before I worked on string field theory,
yes, yes.
as non-local interaction and many other things, group approach to QCD and so on. And when people, I mean, after this, in fact, I was very impressed by this Juan Maldacena paper as well. I was very impressed by Gapser, Klebanov, Polyakov, and separately written paper. We also wrote something in the beginning. Then I moved to high-dimensional model. In particular, I discussed formation of black hole in maybe at LHC. In this case, we study collision of shock wave in high-dimensional case, but in flat case. Just in that time, many people started to discuss thermalization using the geographic approach. This gave me a reason also to work in this direction. So maybe my start was from technical point of view, not just I think, oh, in the nature there are so big questions, I have to do some contribution. No, I just found that I can find the answer to some particular question. After that, I started to learn different proposal, because it was at that time is already not the first, I would say, several waves was in the interest on galography. So I joined this in 2029, something like this. And my interest was mainly about thermalization. So we did several papers. After that, I realized that also first to study thermalizations, it would be good to study static case, just to study phase transition in QCD, and that's all. I really think that this area open and new possibilities. Also now it is very interesting. I cannot say that it's this geographic approach, but in some sense there is a new discussions of information paradox. You know that there is very much information paradox when we discuss the Hawking radiation. Also, there are some problem related with some idea of galography. So this is just an explanation why I study this. There are many.
Yeah, I understand. Yes, I understand.
Questions. Yes. Okay.
Yeah. And in case of Maria, of course, you are the world expert of the latest simulations. And now, yes, of course, technique and, yeah,
No, my motivation was really very trivial. It comes back to my students' day because I graduated in statistical mechanics and stochastic processes and phase transitions. I really love this stuff. I love phase transitions since I was a kid. My favorite game was to melt lead, put in the water and see all the shapes. So I love a change of states since I thought every time I boil water to make pasta, I'm fascinated by vapor. I don't know. I just love it. But then I also love fundamental physics. And I thought, okay, this is impossible because I like two things which are not compatible because I like fundamental physics and I like statistical mechanics. They don't go together. And then I discovered lattice, but completely serendipity. By chance, I got to know these happy people doing statistical field for phase transition. Say, okay, that's my thing. And so this combines two things I love. But then I don't know. Of course, there are questions because clearly in many things at some point you have to call it a day. Because it's true that at some point the progress becomes slow. And then there was a professor in Pisa I really admired a lot, Professor Pietro Menotti. Maybe Irina knows him. He's an expert, great civil theorist. And he used to tell us in physics what's important. You have to understand which are the important problems. And then indeed, this phase transition at high temperature, really how much we want to push it, how many new things we can learn here. So these are important questions. And then I'm not completely sure. I keep on because I love it, but I understand sometimes funding agencies may have reservations. But now I got very much excited by these new machine learning and quantum computing avenues. And so this kind of approaches is a very natural bridge also to these new developments. These are my simple motivations, not very deep.
Yeah, but okay, very good. And also, yes, next time I make up pasta, I will, yes, boil by changing the phase transition, observing the phase transition from al dente to...
And even when you make pasta like fettuccine, and it's amazing. I mean, you start with flour and water, you know how you make, and you start flour and water. And then after a while, you have this beautiful elastic medium. Isn't that amazing? So anyway.
Yes. Yeah. And I think maybe this question is, trivial for experimentalist, but I really, really tried experiment, but from many, using many approach or so how do you invent what you should do, what kind of experiment you will do next?
Sushi, indeed, this is a very good question, and I skipped this question in my presentation because of lack of time. But now I will profit from your question and try to explain what will be the next after this. So, in fact, all LHC experiments started 30 years ago at the beginning of 1990s. And at that time, our physics program was motivated by the theory development which was available by that time. You know, the experiments detectors are not so easy to build, and it took us almost 20 years to construct the apparatus for ALICE, for CMS, for Atlas, LHCP. And then we started working in 2010. After 10 years of measurements, we understood what are the limitations of our detectors, first of all. So the technology was also available 20 years ago, is much less advanced than the technology which we have now. Also, providing the new experimental measurements from our experiments, we push forward the theory development, and then we have the feedback from the theorists. They tell us what to do next, what to measure next. And after the ALICE 10 years of operation, run 1 and run 2, we came to run 3. So run 3 has already started in LHC from the month of July this year. And this run 3 will last till 2025. Then there will be the last run of Alice operation in run 4 till 2032, and we have already upgraded our detectors, and we increased the statistical uncertainty by almost two orders of magnitude. So, for example, in heavy-ion collisions and lead-lead collisions, we will take 100 times more data. It means that our statistical uncertainty, it will be reduced by 10 times.
Yeah,
And then we will provide
yes.
more discrimination power of the measurement. So this is the first step of our measurement for the next 10 years. And this is not all. So now we will think about the next experiment. I told you that ALICE was built during 20 years, and now we are thinking about the experiment which will start on the place of ALICE in 2035, in almost 13 years from now. And this new experiment, which is unofficially called ALICE-3, will be advanced experiment for studies of charm production, charm variance, and also for very soft photons. So these are questions which could not be replied by the ongoing experiments for the moment because the technology is not so advanced. But in the next 10 years, we believe that we will improve not only statistical uncertainty of the experiment, but also systematical uncertainties of the experiment. So the precision of our devices. And in this case, we will be able to measure heavy flavor production in QGP. This is charm production and beauty production. And now it seems the very important question for the QGP properties with heavy flavors, because so far this measurement was not available because of our limited possibility. So you see that we have a really rich program for the next 20 years, till let's say 2040. And I hope that we will study QGP matter from different sites, including also soft photons, very soft photons, and heavy flavors. So this is our future.
And I think today you show also, yes, you will run oxygen, right? Not only copper, but oxygen.
Yes, this is in the program of the high luminosity LHC. So not only heavy ions will be collided, but also intermediate ions. We had a very short run with xenon-xenon collisions. Also, we had very short run with oxygen in run 2, but the statistics from this data is not enough to give any quantitative results. But in run 5 and run 6, there will be the collisions of intermediate ions, and then we will have some data. But for this, we have to wait more than 10 years.
Okay. Vitaly, I think there are maybe many questions from the audience already. Or... Hello. I'm afraid only we are here.
Well, if I can I have a question? Yeah. Actually, I have a couple of questions, both somehow related to vorticity of quark beyond plasma. And first question is to Yuri concerning the alignment of K-star mesons. And indeed, this alignment seems to be too large if you consider it related to quark polarization, because this alignment is a quadratic effect. So just if and lambda polarization is linear effect, so it's too large. From the other side, it's possible to get this alignment not from from independent polarization of quarks, but from its correlations. And we studied this issue just quite long ago. Now, this means that this alignment may emerge due to spin-dependent coalescence. And in other part of your talk, you mentioned that coalescence dominates at small transverse momentum, and when the fragmentation is more essential. And just my question is it possible to relate the transverse momentum dependence of alignment and the transverse momentum effect to coalescence and fragmentation?
So maybe experimentally it is not easy to do because we don't know the underlying physics. So we simply observe the final state particles. And for the interpretation of this spin alignment of K-star, I think it's a good question. So far in Ellis papers, we simply observed that the measurement is not in agreement with the simple theoretical predictions which say that spin alignment should vanish at high temperature. So it was the conclusion of the Ellis measurement. But now, if you say that the spin-dependent quark coalescence can explain this, maybe we have to work together with the theorist and try to introduce some model which will describe this experimental data. And I think this is exactly the purpose of this workshop, to come together and try to address the same question from different sides.
In a sense, quite long ago, just we explained the alignment in PP bar, and in PP bar it is transverse polarization, but with respect to the axis which is along the collision just axis, and this is related to just longitudinal polarization with respect to just axis which is transverse to reaction plane. So just at least qualitatively it's compatible to the just spin dependent coalescence. Although of course there are another interesting effect related to anomaly and so on, and maybe there are different also to magnetic field. So maybe there are different mechanisms indeed related to that, and this is quite rich, maybe just as rich as just polarization of spin 1/2.
Okay.
And if I can, I have just also just questions related to just somehow related to vorticity. Also to Irina, I'm not asking Maria because in the latest there is a work related to rotation, vorticity group also of Victor Baraguta and Andrei Kotov participate. They are working on that. But let me, if I can, just maybe I was asking something like that. Just Irina and her collaborators. Is it possible to see some observable manifestations from the anisotropic metric which you have? So some anisotropy in real space. And in particular, isn't it possible to relate this to say to the anisotropic flows? Just again, even more specific, but probably naive suggestion. Is it possible when you calculate the just multiplicity, is it possible to perform the calculation of multiplicity which is angle dependent? And then if you see this, that multiplicity is changing with angle due to your anisotropic metric, maybe it is some way to anisotropic flows.
Okay, may I ask you the simplest things which can be calculated with dependence of location of phase transition. This is a more evident consequence. So because you just calculate the Wilson line, and if you have some behavior of Wilson line or Polyakov line depends on orientation respect to line of collision. This is a more simplest stuff. Also, there are some really some dependence on anisotropy for cross-section for direct photons. I show this plots during my talk. Maybe it's not enough time to explain. As to your question about dependence of multiplicity, it's usually an experiment. People give us the total multiplicity. And my question is, if people give me a multiplicity, not total multiplicity, but the particles go to some particular direction. For us, I guess no problem to calculate this.
But it is exactly, from one side, this is exactly anisotropic flow. So this is distribution of particles with respect to angle. And concerning photons, which you already mentioned, maybe it is just the way to photons anisotropic flow. Maybe Yuri may correct me. So maybe you already have it.
For photons,
at least for,
it's written in the paper already,
okay.
but for total multiplicity, not yet. But what is I'm worried about multiplicity. Also, maybe this is a question to Yuri, because usually we have a global characteristic. So, doesn't matter at what point, from what point, in some sense, produced some particle. But my question is, it is possible to experimentally distinguish from what part of this how to say this area where is it produce quark gluon plasma or something like this, get some information. Because it is related with total multiplicity in holographic approach, we relate with how to say entropy. But there is very nice characteristic in all this approach, which is called Tangram entropy. Tangram entropy related with some local property. Roughly speaking, it is related with total number if you perform integration of all other possible states, but you keep only information about some particular particle or degrees of freedom produced in some area. My question is, could you experimentally do this calculation, not just dependence on the angle, but just dependent on the point, or not the point. You take a small area and say, from this area, we get this answer, from that area, another answer. For example, if you consider non-central collision, of course, you usually tell me that there are some dependence, but I would like to get more detailed information. Is it possible or not to get information about total number of particles produced in some given area? Doesn't matter how you specified this area, somehow.
So experimentally, it is not possible because we are talking about the area of the size of few tens of femtometers. And of course, there is no such experimental precision to do it. But we can do it indirectly. So we can study different particles which we know are produced from different stages of the QGP evolution. For example, we can study photons, or we can study low mass dielectrons, virtual photons. And we can say that photons are produced at the early stage of the collisions. Then we can disentangle the spectrum of particles which are produced at the initial state, and also particles which are produced in the QGP formation or even at the freeze out. So this is about photons. The same can be said about the prompt mesons and non-prompt mesons. I already mentioned that we have studied separately prompt demesons and non-prompt demesons. And if we look to the non-prompt demesons, they come from the big quarks. And of course, big quarks are produced at the initial state. So there are no big quarks which are produced in the QGP matter. And by differentiating the different particles, we can tell when they have been produced, at the initial state or the QGP matter or the phase-out state. So this is what can be done experimentally.
So you can separate on time, but on space it is difficult. You don't know, no idea how to.
On space it is difficult, yeah.
Difficult. Interesting. Interesting. We have to think more. Okay, thank you.
Yeah, interesting. And yeah, in the audience or in Zoom audience, yes, anyone can make comment or questions or.
To Irina, and actually there are two questions. The first one is more or less technical question concerning the onset of at least onset of at least local thermodynamic equilibrium, because in her talk it was shown the lifetime of this compound, if you want, 10 to minus 23 times something. But what I want to ask, if there are some ideas or estimates of the relaxation times in order to compare it with this lifetime.
You ask me about estimation of relaxation time, okay? Is correct?
Yes.
Relaxation time is usually already at relaxation regime where people use hydrodynamics, so we can use hydrodynamic approach here. So I personally, I don't. We did in our group we did not perform with estimation. Yes.
But in your talk, you showed something which is 10 to minus 3 times something second. Now, during this time, some kind of equilibrium or local equilibrium has to be stated.
In my talk, I mainly describe the phase diagram in equilibrium, in some equilibrium state. In fact, my talk today was mainly devoted to study the equilibrium state. To study formation, we have to study collision of shock wave in this very non-trivial background, which can a possibility to incorporate a phase transition. This not yet done. We perform estimation of shock wave collision only in the simplest Lifshitz type background. So this is not yet done. So because we last year was mainly try to estimate a phase transition itself, not thermalization or not to formation of hydrodynamic regime. Because for hydrodynamics there are very interesting approach also using garography, and it was a very good toy polygon. Good area to ask this question about relaxation. So, but in my group, in our group, we don't perform this estimation. So this is for future. Thank you.
So the question remains open. That's very interesting.
I can, excuse me, I cannot say that I hear you well. I just have to guess what you want to ask me. Maybe my guess is wrong. Could you please use a microphone or some device so to be distinguished? I just guess what you ask for.
Allow me to make one more saying. I mean some comment. May I?
Yes.
Yes.
Concerning the approach which Irina uses so successfully, this holography, I mean, to me, this approach seems up to now seems to be a kind of artificial trick because it deals with some unphysical variable z, for example, which is very important as I can judge because assumption about dependence on this variable is very important to obtain the results. So I believe that this approach is a transitory trick before people will find in the framework inside of the QCD itself how to resolve this problem. Because otherwise it would mean that QCD is incomplete theory. Am I right or not?
In the sense you want to add some quantum gravity, is it?
So no, I don't want the quantum gravity at all. I want to remain in the framework inside the QCD. And if you say me that being in the framework of QCD, it's impossible without inviting this trick as you use holography, I conclude that it means that QCD as a theory is incomplete theory. Is it true or not?
No, assume you are a God. Assume you can solve and you can give me the beta exact. Assume you can give me exact beta function in QCD. Your beta function will depends on quark mass of some external field and so on. In this case, I can tell you corresponding graphic approach. And in this graphic approach, there is a possibility to calculate some objects which are very difficult to calculate in QCD, about which you know everything if you know beta function. For example, assume you want to get Wilson line. Assume you calculated already, you know beta function. After that, you want to know behavior of Wilson loop. In your theory, it's a difficult problem. You have to perform more and more calculation, but in graphic approach, with just a simple one-day calculation on notebook. If you give me exact answer. So in some sense, graphic, of course, I cannot say that this is a five-dimensional coordinate is something which exists in nature. This is not a real five-dimensional real five-dimensional direction, so not an extra dimensional like this. But with zeta, the system is the construction is such that with zeta help you to describe energy scale. So in some sense, you can say, okay, this is artificial trick, like as a functional integral. Functional integral is artificial or not in quantum field theory. Of course, you can suppose you don't know anything about path integral. Question, can you quantize gauge theory? Of course, you can. If you know the final answer, you can introduce some diagram, some constellation of diagram. So instead of Faddeev-Popov ghost, you have to in fact, you can work as Dyson work. You can Schwinger. You can work in Rajcon gauge. Perform quantization in Rajcon gauge. Perform renormalization, and that's all. And you can, in principle, you can calculate what you want. But how many time you will spend, if it will be enough for you, enough time period or not, this is the question. So I agree that the graphical approach is some kind artificial, and this is art. I would say this is art. This is not a nature, this is art. And why not use this to find interesting result. One of, for example, one of calculation of Wilson loop using choreography. This is a very interesting and this related with our intuitive thinking as some strings interaction and so on. A very interesting calculation of entanglement entropy using the Ryu-Takeyanagi formula. You know, to calculate entanglement entropy, this is a very difficult task, even for free two-dimensional model. But if you use, you can use a choreography, then in this case, this is a simplified calculation. So I would say that choreography in artificial trick help us in our calculation. So that's
Thank you. Ira, I want just to add something to your. I understood what you have said. Okay, you agree actually with me. In the last slide of your talk, you used the names from our famous movie Zhiglov and Tarapov.
yes, yes.
And I want also to use some citation from this movie. Есть у нас сомнения, мил человек. I have a doubt. Good fellow.
Okay.
Thank you.
Okay.
Okay.
You have to work more, destroy your doubt. To no doubt, we have worked more. I'm sorry.
Okay, good.
Okay, thank you.
Thank you.
Okay, I think now in Moscow, one, and in Japan,
okay, hi.
Yes,
It's
in
about
Japan now 7.
Maria Paola talk, because it's as I remember, because it's spent some time after talk, but she mentioned that there is opportunity to find signatures of axion in gravitational wave signal. Could you clarify your statement? I mean, please tell us about specific signatures of existence of axion in gravitational wave signal.
Axion.
Oh, thanks for the question. That's really outside my specific domain of expertise. So what do we know is I can tell you the little I know about, but of course many people may know more than me. So from the QCD point of view, what I'm doing is just that I know about a breaking of the Peccei-Quinn symmetry, and then you have all the standard picture of post-inflectionary axion that I have used to define the axion boundaries. Then, of course, model builders, and in particular, I was referring to a model developed by Roberto Contino, for which I can send you a reference, but there are for sure other models, for instance, from the Cambridge group, and I'm sure other model builders have similar results. And then you may cook up models, which of course produce this spontaneous breaking of the Peccei, so which incorporate this U1, this extra U1 symmetry with appropriate extra fields, and then they have this mechanism of spontaneous symmetry breaking that you can study. So in a sense, rather than making reference, as in the standard picture, in the standard Peccei-Quinn solution, you make reference to a generic mechanism of spontaneous breaking of this extra global symmetry, then you invoke a specific build, a specific model that would spontaneously break the symmetry and create this Goldstone boson, etc., etc. Now, at the breaking of this symmetry, you have the main walls. This is standard pictures also for which you have string networks associated to axions. But then once you have a specific model, you can have a specific way of calculating, and then once coupling to gravity, you have a production of gravitational waves. Then you have a specific mechanism that produces gravitational waves. But then how do LIGO people and the future gravitational wave experiment people make a connection. So your question is really very general, because once you have a signal of a gravitational wave in their gravitational wave detectors, how do I trace it back to the origin of the gravitational wave itself? And this relies on enormous effort in matter of simulation, which again uses sometimes artificial intelligence techniques, because you really have to simulate all the possible, what people do, at least as far as I know, many others may know much more than I do. But for instance, what I have learned from Luciano Rezzolla and from the LIGO team who did the analysis, you have simulations of this process. So you have these specific models, like the continuum models in this case. You simulate the signal that you would observe from these specific models, and you have a certain pattern of gravitational wave observation. You change a little bit the model, because the model may have some adjustable parameter, and then you have another specific pattern of gravitational waves. And here there is a big collection of possible signals that you may observe. And what people do, they try to match what do they observe with the prediction of the simulation. And so far, many of these things are done by eye. And I had the chance only recently, I was sitting in a committee, PhD committee, and then the person was really presenting the work on this, and they say they are working hard on developing artificial intelligence techniques to really check for sure how the model is, how can you be sure that a certain signal corresponds to a certain model. So you see, as far as my understanding, is this very important but extremely complicated. There is no such one-to-one signature as I would have in high energy experiment. Oh, I have a peak here and there is such and such a mass. So it goes through different steps. I don't know, I'm sorry to be very vague. I'm not an expert, but that's my current understanding. I'd be glad to hear more from others. Thanks.
Okay, thank you very much. Thank you.
Okay, thank you. Okay, so now maybe almost the time is up, right? And so if
excuse me, can I have a
yes.
small comment, just a small comment?
Yes.
So yeah, I see it. So an effective model approach was not discussed much in the discussion. So I want to make a couple of points. They are quite clear, I guess, but anyway, just to reiterate them once more.
Okay,
you see, yes. What is the drawback or the main drawback of effective model approach? So because it is not a well-controlled approximation, you just don't know what your errors are. It's like 5% or 30%. And it concerns more, for example, NGL model compared to, for example, chiral perturbation theory, where the approximation is much more controlled. But the main advantage of these approaches, because the theory, the models just simpler than QCD. You can have you can calculate a lot of things even analytically, and you can consider a lot of situations that is not possible, for example, in lattice QCD. I guess Thomas could have talked about it, because it not only concerns the baryon chemical potential, where of course lattice simulations not possible, I mean, now. So and it concerns even, like, for example, two-color QCD. You know, you can consider on light. There is no sign problem for two-color QCD in real QCD, but if you want to consider, for example, baryon chemical potential and isospin chemical potential, all the stuff, you cannot do it even in two-color. But in effective model approach, it's possible. You can consider a lot of chemical potentials, like magnetic fields on the stuff, and calculate things, and you can hope to qualitatively describe the situation, at least qualitatively. So it's just a small comment, sorry.
Yeah, okay, thank you. Yes. So is there the last comment or last question?
Okay, maybe a short question to Maria.
Yes,
Maria?
please.
Maria, you said that the tricritical temperature should be below the critical temperature for chiral limit. What is
The
the
critical endpoint, the temperature for the critical endpoint.
critical endpoint? Yeah, critical.
I also the tri-critical temperature also, of course, both of them. So the hierarchical would be top the critical temperature for the critical endpoint, lower the tri-critical temperature, even lower the temperature of the critical endpoint. If this O4 symmetry scenario is respected and if there are no very strange behaviors. Yeah, actually, for instance, in NJL models, as to follow up previous comments on which I completely, absolutely agree, these things, I don't know whether they have been checked explicitly. That would be very interesting. So please, sorry, Vitaly. Yeah.
Okay, thank you.
Okay.
So we can.
Yes.
So please, your final words.
Yeah, but anyway, yes, yeah, really, at least I can learn, yeah, many things from the discussions. So I appreciate, yes, all contributors and speakers. Okay, so now have a nice lunch in Europe and yes, in Japan now. Yes, I will take yes, dinner with my family.
Very good.
Okay.
Thanks a
Okay.
lot.
So
Thanks a lot, Susan.
Thank you.
Thank you very
Thank you.
much. Thanks a lot, everyone.